Thank you, Star. It's my pleasure to introduce Tom Hagen, who is now working as a breeding software product manager based at the CIMMYT campus here in Mexico. Tom received his PhD in plant breeding from the University of Georgia and later worked there in the Department of Microbiology on several different initiatives, including founding and managing the UGA Center for Scientific Computing and Visualization. He later moved on to work in DuPont Pioneer as a research information architect. There, he had many responsibilities, including conducting precision phenotypic and phenotypic analysis and crop growth modeling research, consulting with data scientists on applying breeding trial results to on-farm yield response classification and product placement and management analyses, advising trait research scientists on effective trial experimental design, execution, analysis, and decision-making, and leading the design effort for the unified analytics system, providing integrated phenotypic, crop growth model, and whole genome analytics for the trait breeding and digital ag research organizations. Tom transitioned to his new role within the CG earlier this year, and we look forward to hearing his talk today on improving the predictability of breeding programs through an enabling enterprise breeding system. So please join me in welcoming Tom.
Well, thank you, Kate, and certainly I want to thank the GOBii community and CIMMYT and EIB and I guess especially the individual I work most closely with at Pioneer, Mark Cooper, who created the environment for me to do this science and IT, and the great people I got to work with there. So today's seminar is really focusing on what we're going to do and how we propose to do it. I envision this is the beginning of a discussion because we'll be collectively working on this for the foreseeable future. And so certainly anticipate many follow-up discussions of various types. I also want to mention that I will episodically skip over slides because I put certain slides in there in case there is a follow-up question that we want to have a slide to go into more detail. Let me just sort of start with what I mean by integrated. And a system, the system that is required for the objectives that we have to improve the predictability of breeding require various types of integration. One is of all of the appropriate information that's necessary to conduct breeding, interpret outcomes, make decisions, but also the functionality. People are conducting workflows, and so you need to deliver that functionality in an integrated workflow step context. We're also following a sort of a hybrid development model that's somewhere in between designed and agile, where we have the concept of development phases and with specific objectives, but those phases are targeted, prioritized elements of an overall system architecture or design. We're also going to use a strategy of first or early adopter breeders that will work very closely with us in terms of defining practices, necessary capabilities for executing those practices, setting priorities, and help us figure out what we didn't get right when we release software. To me, it's always good to have a definition of what is success, and one critical definition is that it's something that breeders use as a regular part of their work. It helps them efficiently conduct the necessary operations, but also is generating the information not only for them to interpret the outcomes of their trials and design the next season's trials, but more broadly collect information from across all of our trials so that that is our knowledge, how we learn and get better. I want to start with the beginning point. To conduct breeding to attain genetic gain, we have to have a clear concept of what are the environments that we're breeding towards. What are the product concepts or performance characteristics and evaluation criteria in these target product environments. That then leads to us how we need to characterize, define germplasm in terms of phenotypes and the physiological behaviors or characteristics that yield those phenotypes. how we connect that information to genotype and pedigree, and ultimately then what happens when it gets to the farm. And that cycle then will run over and over again. To kind of give an example then of how we begin approaching that, we can ask ourselves, so what's the gap between what we anticipate our germplasm to deliver and what the farmers are actually attaining? And so by getting those assessments, then an important part of breeding is to starting to deconstruct that signal, identify and evaluate or characterize what are the important features of those gaps. And that, of course, leads to then the design of our breeding practices, the selection of germplasm, how we evaluate it, and of course, identifies critical features of a breeding system. To kind of give a very high-level outcome, I mean, this slide represents a good 10 years of research and development and corresponding IT implementation by the May-Stress Product Development Group at Pioneer, which I had the privilege to work in. And so just to kind of highlight the slide here, that there's 4 key elements, and this axis here is a drought concept. This axis here is yield or performance concept. And so the idea of this is that whether you're a breeder or a farmer, what are your actual results for a given trial location year? And up here, we're representing what is the potentiality of the germplasm that we've determined from our breeding trials. And so that's the yield gap. And so there's really 3 key actions that can happen from there. If you're the breeder, then that helps you guide your choice of germplasm to go into your trials. It helps you guide how the design of those trials for evaluating that germplasm, and the choice of locations in which you are evaluating. If you're the extension or agronomist, then it gives you that understanding of the interaction between hybrid and environment by management, so you can then advise farmers as to what would be appropriate germplasm for their circumstances, and that those trade-offs between management, economics, socioeconomic conditions that they live in. And then finally, if you're the farmer, that gives you the range of environments in which a given, or fields of their fields, that a given germplasm will give a stable or reproducible result. Now, of course, this is something that, again, it took us a while to get to, so I want to go through then how we get there, because we don't have to get here all at once. By creating the system and beginning with where we're at, we can build towards this, and the system will help us conduct these operations and generate the information that helps us get there. Now, this process requires very complex workflows, and so that's an important feature of the system, that, of course, it provides these capabilities, and again, in an integrated fashion. Each step of the workflow has given activities that are necessary, integration of information, integration, if it's not just one person, there's teams of people working across this. And, so these are very important design characteristics of a system. What would such a system, look like? It is a workflow system. Of course, there's different steps of the workflow, from design to ultimately what's gone to the farm. So we build the system, or design the system, to provide these integrated capabilities for steps of a given breeding process. And technically, it's a tiered system. We have primary data. I mentioned the term modular extendable, so you can think of different types or domains of information as modules that we can plug in. And that enables not only new ones coming along, but if we need to change something, everything is not unduly or tightly coupled. We have then data access layers, and we can access this information in different ways. There's not a singular data access layer. If you're doing trial design, you'll access it one way. If you're doing analytics, you'll access it a different way. And so we have multiple ways of accessing data. And of course, there are primary results, and we have to transform or recapitulate them or synthesize them as the actionable information that then people consume. And of course, we also need to have modular different classes of analytics. And of course, certainly the two that are be our prioritized starting point is exploratory, because there's always the need to bridge a gap, to discover something, to validate something. And then there's the more formal in-system analytics, starting with phenotypic prediction. And of course, then there are the applications people use and the knowledge that we're generating over time that's used in activities like program management, germplasm selection, extension, big data in different ways. So here is just a highlight of a generic breeding workflow. This is an important element of an architected approach, is that you have a transition from what do people do to the system. And so by identifying key activities of a process, either at a very high level or when you get down to a very specific module or software element that you're going to design, of course, it gets increasing layers of specificity. But this is the key mapping between what people do and the capabilities of the breeding system. The other point I want to make is that there's not a singular process, that it would be a mistake to force people to behave the same way, because we are breeding different crops, we're breeding in different environments, and so we have to have a system that has generic logic but supports the variations on the theme that are necessary. And that not only is enabling the activity of a given breeding program, but by having these things unified in the system, that it enables the sharing and leveraging of information that we need for ongoing continuous improvement. So how do we start mapping these workflows to system functionality? Well, then when we need this is not necessarily a data model. What we're doing is identifying what are the key concepts of a workflow or breeding practice, their relationships, their logic according to these steps. And again, at a high level, you start with a product concept, and when you choose actual so this would be, for instance, certain degree of yield under a certain degree of stress. But then when you choose germplasm, you're really kind of at the level of not just phenotype of germplasm, but what may be the physiological responses of that germplasm, the genotypic characteristics that deliver that. And that, of course, then leads to the trials or experiments you're designing, and they have defined objectives, testing procedures, statistical designs. That, of course, then leads to the appropriate choice of locations, the appropriate choice of traits or phenotyping. And collectively, these concepts, experiments, locations, traits that define what is the inference you're testing for a trial, and therefore the analysis protocol, which in turn defines your statistical models, and so on and so forth. And that then generates your analysis matrices, and you get the results. And given in the context of these product targets, that gives you structured information for making the types of decisions that you need to make for a given breeding trial. How does this then map to proposed system modules? Of course, we've got program management, the ability to create these trials, whether it's a nursery to implement it in a nursery location, whether it's an actual breeding trial proper in a trial location. Nurseries, of course, generate seed information. We need the ability to genotype either plants in a nursery or seeds, and of course, genotypic data management, which is the GOBii project. And that comes back to your experiment creation, where you've defined that starting array, and now you've collected all of the outcomes of executing on that array, and that then feeds into your analytics. And of course, there's different reiterative cycles across analytics, and that ultimately leads to the capture of primary results and those structured results that go both into decision making, or again, this is our big data for analytics. And I want to mention that we're roughly following 3 high-level implementation phases. Of course, the core of this is the ability to create these experiments, whether they're nursery or trials. And so that's very much one initial critical phase. The other is the ability to genotype those. And I'll say the third is the ability then to conduct analytics on that. When you start converting this into system data exchanges, you have these high-level elements of an architecture, and you can think of this as object-oriented programming, where you've bound these as edges, and then in between these edges, you have these data exchanges. And some of these will be EIB level exchanges, and of course we're going to focus on GRAPI calls for those. Some of these are within system changes, and so the team working on the system is going to decide what's the best technologies and means of negotiating those exchanges. And then we have analytics. They're a third special case, because in analytics you need to create interim data stores, because any given analytics will cycle over that data. Each iteration of that analysis will identify elements of that data array that need to be suppressed or adjust the model in different ways. And so that is not just a straight up GRAPI call or ETL process. That's too inefficient. So that's a third class of data exchanges that we'll have to think through. And again, we're roughly having 3 phases. You could sort of think of this stack here, where we're going to focus on the GRAPI calls around that. We'll again define these edges. What then is the information being exchanged? What's their model? What's reference data sets? What are the GRAPI specifications? What is a concept of unit testing, integration testing, how we deploy, deployment acceptance testing. So we'll use this stack here as a good use case for thinking through more formally how we do this. And then we'll extend it. I think this will be our second stack, and this will be our third stack. I want to transition a little bit to talking a little bit about the science and how the system enables science. And I like to use the word predictive breeding. How do we generate information that we have confidence in to make these decisions? Germplasm selection, ultimately what to give to a farmer. And so this is a process of continuous improvement, where we're operating, conducting breeding operations through the system, collecting information about them, accumulating that information, and we could episodically look at that information, typically once a year, or once we've conducted that year's rounds of breeding trials, and ask ourselves, well, how well did we do in germplasm selection? How well did we do in trial designs? How might we want to tune our statistical models? And you come up with a list of where in your process is the error. And you just prioritize that. And sometimes you may have to have a discovery project to investigate trial designs or ways to improve phenotyping or ways to improve planting. Of course, it leads to software development deliverables, but just a process of continuous improvement to identify where you're introducing error that degrade the quality of your predictions, and since those predictions are the foundation of any breeding decision, the more error that contain, the less reliable or confidence we have in them. And so just an illustration of this is a phenotypic analysis, and the bars represent different varieties. Some of them are test entries, 2 different check entries, and these are their predictions for a given trait. And then the error bars are the standard errors. And you can see that this particular variety has a high standard error. So in reality, the behavior of this variety is in somewhere in this zone. And so you would not be able to reliably or reproducibly differentiate those varieties. And so if you made a decision on these varieties saying that, well, this one is better and this one is worse, that would not be reproducible. If you repeated this trial the next year or under similar circumstances, you get a totally different pattern of results. So it's very important then that we detect error and drive it out. Otherwise, we'll not be able to get the heritabilities and genetic gains that we're seeking. So I'm going to skip over these two slides and kind of focus in on, well, some are key steps. There's many steps to detecting error, but I'm just going to highlight some of them. One of them is our information models. This is a high-level conceptual model of germplasm, and it's necessary to correctly define germplasm. Each seed is in reality a genome, and so we need to consider as such. And by so doing, that allows, we then have the correct data model, software artifacts implementing that model that allows us to seamlessly integrate work in genotyping, phenotyping, pedigree, whatnot. Without that, then the data is orthogonal to each other, and we'll always struggle with connecting those dots and, again, having reliable software operations, reliable driving out of error. But also, we're supporting 4 key domains of activities. Of course, nursery trial operations, gene bank accession, reporting decision-making, and ultimately knowledge discovery. So accurate data models are essential to this process. And so certainly then, one of the things I'm bringing to the table are these models for the system. And getting back to what I mentioned in an earlier slide about BRAPI calls, data exchanges, that we have to have, again, if it's just within system, that's okay. But as soon as we start getting to exchanges of information between system modules and try to implement those technologies for doing that, we have to have alignment on data models. This is the high-level model of what is a place. And it may seem simple. Well, there's just location in the field here and it has these lat-long coordinates. But in order to correctly intersect the germplasm that's there, the place concept proper, the processes for sampling and collecting measurements and deriving values from them such that you can do appropriate analytics, it's not at all simple, particularly if you think about that. We have concepts of plot, location, field. We collect data not only by traditional plot, range row coordinates, by geospatial coordinates. We can have a measurement of a plant or part of plant or a part of a plot. We can have a measurement of the whole soil zone that is overlaying a location. So how do we put that information together so we can use it in not only analyzing a trial, but understanding ultimately that G by E by M equation and those recommendations to a farmer? We have to have the models that, again, support these operations. And another important concept here is the thing you measure is not, and that value is not the trait of the object you analyze. And so you have to bridge between those concepts. Again, otherwise you're creating not artificial, but you're hardwiring joins, and you inherently have a non-scalable, extendable system, and you're limiting from the get-go the capabilities of the system. This is for that slide I showed you of the target product environment hybrid cloud. Another important concept to introduce is that you don't ever have a singular trial. If you try to have a singular trial, then you're putting too many different inferences into that trial, and typically so that none of them is optimal. And so the best strategy then is to have a set of experiments, and this is a critical element of then the trial design functionality, that you need to allow breeders to create these sets so that each type of experiment has a focus objective and the appropriate relevant designs. And you can then combine those outcomes from these, whether it's primary data going into analysis or outcomes from an independent analysis of each. And at a high level, you'll have, of course, your primary yield trial, but to dissect GBI/M, you'll have an associated trial focused on that, where you have come up with a well understood phenotype or physiological behavior. You can put that into some type of phenotyping assay, and then to have your location assessment across years, you can have some side tester type experiment. And to enable this, then, it's important that we define the metadata of the different elements. Here's just an example of experimental metadata, and that by having these, the particular values you would have for any of these concepts would vary by breeding program, but the software behind the scenes is generic. And so you come up with a unique combination through the choices of pattern, not only by breeding program, but by type of experiment, by stage of the breeding process. But also then these become actionable, that once you've created this trial and captured this metadata, you can use it to guide planting, to guide management, to guide phenotyping. You can use it to guide assembling that information for different types of analysis. You can use it to provide a context to those analyses, so you can then use that in decision making. And ultimately, it's through this metadata for not only experiments, but also other things like locations, trials, germplasm, that we are creating this data store over time that is our knowledge and will mine to understand or conduct this continuous process improvement to get better predictability. I want to propose phenotypic analysis as a starting point because it is the foundational analyses, not only for the interpretation of a given breeding trial, but it is the empirical evidence that we'll use to develop other types of analytics, such as modeling, big data, and activities like environmental classification or remote sensing. So anyway, it is the essential analysis. And I won't go in, I'll probably skip over this a little bit, but of course the recommended outcome of phenotypic analysis are BLEPs. And I do want to touch a little bit on this slide is that in phenotypic analysis, and a key element of reducing error is driving out spatial variation. And so phenotypic models can handle very well through understood methods how to model and therefore manage this variation. And a particular way of doing it is row column and AR1 spatial adjustment. And so that's a critical element of the phenotypic analysis that we'll initiate. And just as an example of that, if you have unadjusted means, this value is including not only the actual genetic performance of the variety in this plot, but that spatial variation. And when you then go through this spatial adjustment process, you're adjusting those values. And so that's why unadjusted single location means are not reproducible. You cannot make any accurate decision on them. And so here's an example of one of these GBI/E/M experiments. I've got 4 drought stress levels. Each is replicated twice, and within each I have population densities. We're looking at the interaction for a given germplasm of stress by population. And so, of course, the statistical software we're going to use to initiate phenotypic analysis is going to be ASREML. And we can do this in a very generic way so that, again, given that trial metadata I defined, it just, in effect, calls, all these concepts so that you can connect the appropriate analysis model to a trial. And of course, we then will have metadata. There's a whole new class of metadata that defines in the analyses and the, in effect, type of inference or what these results represent, and of course job management. The models are built up, you have an array, and so this is where you're specifying the columns of that array, that ultimately leading to the actual model. And then from that model, you can generate different predictions. This one would be the overall phenotypic inference. And here you're looking at how the germplasm interacts by population density and stress concept, and anything in between. And so, and in here then is my row column and error one spatial adjustment. So I'll skip over this one. I'll skip over this one. This is just an example of how formal it can get, that at a given stage of evaluation, aside from this concept of type of experiment, for your main performance evaluation experiments, which typically is yield, at an earlier stage, you'll just have perhaps a singular experiment, and it will be in different locations. But at this later stage, or this pre-commercialization stage, you'll be having these experiments. This is a zone 2. You'll have a zone 1, a zone 3, ultimately up to zone 50, and you'll have these combinatorial experiments in these different zones that are unified or aligned by checks, not only across a year in zone, but also then across years. And so this is just an example of the type of experiment design capabilities that we're going to need. I want to next talk a little bit about phenotypic analyses. Our trial analysis is that at present, we're creating a lot of pipelines, which is very necessary because, we need to be able to analyze our trials, but by being standalone modules that the input data is not well defined, and so we're spending too much time, curating that data, and the outputs are not real well defined. And so we want to work towards where we can plug these analysis modules into the system, because not only do they allow us to have singular development activities, these in effect become services, so our software develops more efficient. It allows us to increase the timeliness or throughput on trial analytics and do more of them, and ultimately facilitate learning. And aside from just better analysis per se, it's that we all know that plots are very expensive, and if we don't have an efficient way to conduct analyses, then we're not extracting all the information from it. And so it'll be very hard for us to know specifically how the predictability of a given trial, but also we'll not be able to collect this information over time and use that and more broadly in this continuous learning process. And also then it really means that it's not that everyone doesn't have a very good understanding of their trials and information, but they know it. No one else really knows it. And so we're not really being truly data-driven. We're too subject to more anecdotal or informal information. So I'll skip over this one, maybe this one. So how are we going to propose to to do this? That there's a concept of a trial analysis request. And again, if we, by creating the trials in the system, we have the metadata that define what program am I, what stage am I, what inference am I testing. And that defines then the source data you need, but it also connects to the appropriate analysis module that both of them which specify what's that input array. And so these things in green here are elements of the analysis module that you saw in that very early on high-level system diagram. And so these then are generic. They're readily can be called on or used by our framework in which we can drop in these analysis modules. So certainly that all the work, different biometrics and bioinformatics and different projects like what we are doing, will provide then a framework that they can drop in these analysis modules to execute and capture the output in primary results. So the things in green here will be, in common, and again, this will be specific modules. And since there's always a need to do these out-of-system or exploratory analyses, I want to make that easier also. Don't hear me saying that I think it's inappropriate. It's absolutely necessary. We just want to not use these for these and these for this. We need to have clarity around that. But by building this framework, then, that the struggle that these things have of getting input data would be a way for us to help solve that problem, so we can actually scale out of system analysis, because again, they're essential for, we need to provide some bridge functionality, or we're working to develop or validate a method, or there is just sort of a one-off R&D project. So that's critical. But then from this come these modules that we've agreed now that this is the appropriate methodology to use for analyzing a given type of breeding trial. And so then that these will drop into here. And this analysis framework, I don't want us to assume that we'll do everything, so that we'll, again, start with phenotypic analyses. So we'll create this framework first, and then as we go on to other domains of analysis, the actual technical framework will be different, because the actual logic for each of these is different. But these plug into, again, here's your source data, analysis-ready data, primary results, reporting, and visualization. So these different units here will plug in to that overall framework. So this would then be an example of a phenotypic analysis module. The separate module then is these knowledge modules, where you're, again, putting together primary results for different types of decisioning operations. And this is a detail that I'll skip over this in case we want to come back to that. But I want to mention knowledge representation, because at the end of the day, we have to be able to understand what it is we've done. And so, that the outcomes of a breeding trial is a fitness or performance landscape. And here's a conceptual example of that. And to actually see an actual visualization like that TPE cloud I showed you, or some others I'll show you subsequently, we're projecting, from this, this fitness landscape. So you can think of each of these as a particular window onto the overall fitness landscape. And so in order to translate data to information to knowledge, of course, we need, starting with our data models and our tiered architecture, we need, of course, to have primary data management of our sources. And then, we need to, of course, provide that to analytics like I highlighted, and then we're capturing those primary analysis outcomes into reporting data structures in some type of reporting database. And so so in each of these, from primary to analytics to interpretation, has different types of models, but they are all the concepts connect across from them, but the physical implementation in these different layers, source, analysis, knowledge, are going to be different. And the designs of those systems in terms of how they manage and organize that information will be different. And then we're going to create by domain or workflow step, what is the types of decisions that are making, and therefore what are the visual representations. And of course, we can have an overall meta representation that we can use for big data and whatnot. So as an example that's sort of focused on actual trial decision making, is that, of course, we've all can see the, the kind of the classic, here's the thing I'm evaluating, you have a list of them, here's the performance, and by your product concept and your product evaluation or acceptance criteria, you can say, okay, well, these are yes, So that's clear, you don't have to spend too much time on those. These are no, that's clear, you don't have to spend too much time on those. And here's the ones that are in between we have to discuss. And that's where other associated information in terms of the characteristics of a trait, characteristics of a location, characteristics of a germplasm, and these other types of analyses that I mentioned. We can have the overall phenotypic inference, but we can also then have how germplasm is interacting with EBS, understanding of heritabilities, location variances, things like that. So we can project into this type of visualization or knowledge representation framework, not only different types of analyses, but also both direct results of analyses and calculated values based on those results. And so something how this would work, we have this, this concept, we have this set of experiments, each of which has a tuned design, a tuned implementation, and therefore a tuned analyses. And we can then capture the, so these then, again, there's the experiment metadata, the analysis metadata, in effect defines what type of analysis outcome we have, and so we can project that into these advancement panes. And here's my overall phenotypic inference. Here's my interaction inferences. Here's my germplasm composition inferences, and information about variability, repeatability, things like that. And so, how might like something that look? Here's an example of a decision grid where you have different types of experiments and just the primary phenotypic or overall inference from each of those. And of course, we can have, these represent different entries in that trial. And here's my sense of performance threshold or acceptance. And you can have some concept of a control there. But we can also project these into grids like this where we have interactions between these different traits and also interactions between attained performance, optimum performance, expected performance to get at these gaps that I mentioned earlier. And so we could not only visually represent them, but we can also apply analyses to these, obviously the mind's eye can be deceived by patterns. And it's not that you don't want expert making informed decisions, but we can also apply analytics to these to capture out information on top of the primary analysis results. And ultimately, you could project that into some type of decision-making grid. And so one way to, let me come back here, we want to, we're talking about then capturing these results into here and creating these reportable data structures into these decisioning. And so one thing that we were starting to explore is the use of a BI tool like Tableau or Spotfire. And part of it is that the magnitude of the software development to create this rich set of visualizations is quite large. And we need to focus on the very first slide is, so we want to take a system integration approach. And so we have to focus on building the core logic of the system because that's unique to us. But there are elements that we can plug in. It may be an open source thing. Certainly there's many robust open source features. It may be a commercial tool, but we'll make judicious choices about what can plug in. And a BI tool is a good example of that. Not only does it have out of the box the features we need to create all these different types of visualizations, but again, allows us to focus on what is unique to us, what we must do. So here's just an example of from a BI tool of sort of a classic field heat map, where you can see the variation of trait responses, either pre or post analyses, and how that goes down your row and columns to give an estimation of that field spatial variation. And here's an example of a very complex analyses where we have a trial in 3 different locations. And I'm just showing you one of the testers, but there are actually a panel of 5 testers. And we had a set of about 100 traits. And so we did overall analyses, and we could put all pieces together to help us understand the interaction of germplasm by location, by tester, by trait. The last thing I want to mention is that by conducting these analyses in system, we're capturing a significant amount of information. Not only that's what's used for the actual interpretation of the trial, but here's an example from a factor analytic ASRML analysis, the correlation of variance covariance. And here then would be a location, and you can see that it, supposed to be 1, 2, 3, this would be 2, so you can see that there's a high correlation in genetic response between these two locations. But this would be 1, 2, 3, 5. This is a very low correlation. And so this helps you not only understand, I'll say, the informativeness of locations and stepping back to the very beginning, if you anticipated that you were evaluating, say, 5 different location concepts, this would help you understand how well you actually had done that. But also this pattern of various covariance correlation allows us then to start exploring concepts such as environmental classification and other approaches. So it's a foundational analysis, not in terms of feedback as to the outcome of a trial and your choice of varieties and locations and traits, but again, it helps us build towards the future. And ultimately, we're going to lead to where, by capturing that information and think through things like regular arrays of check experiments and whatnot, we can capture, well, here for a given location or target product environment, what the overall distribution is. It has some total mean behavior, but what did I actually get for a given year? And of course, we can have the individual location, performance, the overall phenotypic inference from across other locations, and from that multi-location analysis, a per location analysis to get a sense of the interactivity of the location, of that germplasm of location. And so we can use that then to both not only help us put a given year's results in context. Am I towards the negative tail of my overall distribution, therefore my performance may actually be better than I think it is, or am I at the positive tail, then I don't want to overinterpret. But also then this derives information that we can use to begin to classify these environments. And by classifying not only trial locations, but on farm locations, it allows us to project our research trial data onto the farm and start making, again, this assessment of what's the potentiality there, what type of recommendations would we want to make to that farmer in terms of what to grow and management practices, but also allow a different type of analysis. Typically in a trial, you're asking, how is my G behaving by E, M, whatnot? But to the farmer, you want to know, for a given hybrid, how's it going to vary by his particular E and M? And so it allows us to just, in fact, rearrange the concept in the equation and do a very informative analysis. Anyway, and then beyond just phenotypic analysis, of course, we can have calculated values, and we can go beyond univariate to covariate, bivariate, multi-trait, and also I'll just use a loose term, multivariate analyses to again start extracting the signal not from a given trial but from across trials. And in terms of development process, we want to have a breeding advisory team to help us understand what are the important objectives and practices, and oops, it should have been, I repeated myself. This would be the architecture team, to map breeding practices to the system, and then, of course, the actual development teams. And then we have these different phases: design, development, deployment. And we'll sort of take this concept of, with these early adopted breeders, a minimum viable implementation is through a number of cycles. We'll get the system to a certain point where it is in the context of the overall design, but we've created this minimum viable implementation that then, as we start adding more breeders, more other programs, whatever, we can just be in a very stable, define new enhancements, features, whatever, and just be in development. So that's where I want to stop and ask questions, and just to kind